so thanks for coming, everyone. So I'm going to follow on about hypothesis testing. We're going to be talking about simple hypothesis testing in this. This is joint work with Clement Clement, Gannon Kamath, Adam Smith, and John Allman, all of who are here with varying density this week and this semester. Okay, so Jordan just talked about hypothesis testing. Let's do a little bit of a review. So hypothesis testing happens everywhere in statistics. So we have here our data analyst, and she wants to know the answer to some yes or no question. And one way she might try and answer this question is to construct it as a hypothesis test. So in a hypothesis test, I have some space of distributions that I think my population could possibly be drawn from. And I have two sets, my null hypothesis set and my alternate hypothesis set, that are disjoint subsets of my space of distributions. And the job of a hypothesis test is to take some number of samples from some distribution R and decide with high probability whether R belonged in the null hypothesis or the alternate hypothesis. And these tests are ubiquitous in statistical inference because they formalize yes or no questions about an underlying population based on samples. Okay, so my data analyst here wanted to know, do at least 50% of people support Democrats? Insert your favorite yes or no data analysis question. But what she could have asked is just, is the probability that someone supports the Democrats 50%, or is it 49%? And for most hypothesis tests, if she answers this question, she will have also answered the previous question. And this is a simpler kind of hypothesis test, aptly named a simple hypothesis test. So in a simple hypothesis test, my null space and my alternate space are just singleton sets. So I have two distributions P and Q, and I'm just trying to decide whether the samples I get come from P or they come from Q. And why we care about simple hypothesis testing is there are a couple of reasons. So one is that we can see that many composite hypotheses, so composite hypothesis is just where H0 or H1 are not singleton sets. Many composite hypotheses can be reduced to simple hypotheses. And because this is the simplest type of hypothesis testing, lower bounds for simple hypothesis testing are going to apply for composite hypothesis testing. And they also arise in lower bounds for estimation problems. Okay, so this slide is a little bit preaching to the choir here. But it's often desirable for statistical tests to be stable under small changes in the data. So one of the reasons we care about this is privacy. And a nice line of work done by several people in this room says that we might also care about this if we care about generalizability under adaptive data analysis. Okay, so unless you've missed every talk this semester, you probably know this definition. We're going to be talking about pure differential privacy today. So a test is epsilon differentially private if given two databases that differ on a single element. For any given output, the probability of that output if the input was x is about the same as the probability of that output if the input was x prime. And what is nice about testing is that the optimal sample complexity is the same for pure differential privacy, approximate differential privacy, and hence any stability notions in between. And these include concentrated DP, KL stability, and total variation distance stability. So while I'm going to focus today and phrase everything in terms of epsilon pure differential privacy, all of the bounds I'm going to say also hold for these other notions of stability. Okay, so as we've seen, there's been a lot of work on private hypothesis testing. So some of these focus on producing differentially private versions of popular statistical tests, such as goodness of fit, closeness, and independence. Some focus on small sample sizes. Others focus on asymptotic sample complexity, which is what we're going to talk about today. And most of these are in the central model, and there's some work in the local model. What is maybe different about this work is that we're going to give an instance-specific sample complexity. So that P and Q we're trying to distinguish between, the sample complexity we're going to give is in terms of P and Q. And as far as we know, this is the first work that gives an instance-specific characterization of sample complexity in the central model. In the local model, Ducci, Jordan, and Wainwright give an instance-specific characterization for the same problem for simple hypothesis testing, but in the local model. And we'll talk a little bit more about their result a little later.
So what is the instance?
The specific P and Q we choose. So we've talked kind of intuitively about what hypothesis testing is. So let's get into what it actually means kind of mathematically. So we say a test is going to distinguish between our distributions P and Q if, given a sample that really was from P, it should output P with probability 2/3. And given a sample that really was from Q, it should output Q with probability 2/3. If 2/3 doesn't seem very high to you, we can amplify this to any constant with a constant factor increase in our sample complexity. And I've said this word sample complexity a few times. So the sample complexity of a test is the smallest n such that if I have a database of at least that size, my test always works at distinguishing between P and Q. So it always satisfies these two things. And I'm going to say a test has optimal sample complexity if its sample complexity is big O of any other test. Okay, so I'm talking about asymptotic sample complexities. Okay, so today we're talking about private simple hypothesis testing. So everything kind of remains the same on this slide except for the blue things. So we're now going to require our tests to be epsilon differentially private. And I'm going to put this little epsilon on my sample complexity when I mean the private sample complexity. And now, of course, I'm going to call a test has optimal sample complexity for a private test. I'm only going to compare to other private tests. And so a big part of the question today is going to be how does this sample complexity change when I change epsilon or put an epsilon in it at all? And how does the form of the test change? Okay, so there are two main contributions of this work. So the first one is we're going to characterize the optimal sample complexity for privately distinguishing between P and Q. This is for any distributions. We do require them to have PDFs, but other than that, we have no requirements. And we're going to give actually two optimal efficient tests. So two tests that achieve this sample complexity. I have a star in the efficiency here because there's one little caveat to how efficient they are. We'll talk about that a little later. Along the way, we're going to give a novel interpretation of the Hellinger distance, which is going to give us some insight into the non-private setting. In the paper, but I'm not going to talk about it today, we give an application of our hypothesis testing result to epsilon differentially private change point detection. Okay, any questions so far? Okay. Okay, so before we get into the private result, let's talk about the non-private solution. So if you're given a database and you want to decide whether it came from P or Q, and you don't care about privacy, what you should do is just output P if it was more likely to have occurred under P than Q, and Q otherwise. And a famous Neiman-Pearson lemma that Jordan mentioned says that this has exactly optimal sample complexity. So notice I have this word exactly here because there really is no test that's better than this. And its sample complexity has this neat characterization. So its sample complexity is determined by its 1 over the Hellinger distance squared. So how we define the Hellinger distance is if I take my distributions P and Q, if I take their pointwise square root, they lie on the unit circle. And the Hellinger distance is the Euclidean distance between the square root of these distributions. So if you don't have a lot of intuition for this, part of what we're going to talk about in this work is giving some intuition of why this particular distribution occurs, or this particular metric occurs in the hypothesis testing problem. Okay, so one thing I want to do first is I defined this test before. This is kind of the most obvious thing you could do. But I actually want to rephrase it like this, where I have a test statistic, I'm going to call it the log likelihood ratio, and I make some decision based on my test statistic. So what my test statistic is it just takes every data point, it takes the ratio of P over Q, it takes the log of that and sums them all up. This is exactly equal to the log of Pn of my big database X over Qn of my big database X. And so if this thing is bigger than 0, that means that X was more likely under P, so I should output P. And if it's less than 0, then the same for Q. So this test is exactly the same as the test I just described. It just has this test statistic that's going to be a useful way of writing my tests. Okay, so the reason why the Neiman-Pearson lemmas may be so famous is because this is a really helpful lemma if you're trying to do actual hypothesis testing. So it means that you should, if you can, you should definitely do this log likelihood test, and you shouldn't worry about doing anything else. So our goal for today is going to obtain an analogous result for private hypothesis testing. Okay. short outline of our talk. So we're going to state the main theorem, always helpful in a talk. And then our proof is going to come in 3 parts. So the first thing we're going to do is give some insight into the non-private test. This is going to tell us a little bit about how we should construct our private test. And then we're going to do an upper bound and a lower bound. And we'll talk more about how they're actually going to go a little later. Okay, so this is not quite true. I'm actually going to lead up to the statement of the theorem. So first, let's talk about what your first guess of this thing might be. So this thing is easy to prove that it's a lower bound. So my private sample complexity is definitely bigger than this. And I have my non-private sample complexity plus 1 over epsilon times the total variation distance. And why this says lower order here is because if I got rid of this epsilon, this first term would always dominate this second term. And this is a kind of form of sample complexities we see often in privacy, that we have the non-private sample complexity plus some term that depends on epsilon. So it turns out that for Bernoulli distributions, the upper bound also holds. And this formula characterizes the optimal private sample complexity. And this is really nice because it implies several things. So the first one is it implies a phase transition. So it means that if epsilon is bigger than your Hellinger distance squared divided by your total variation distance, then you get privacy for free. What I mean by privacy for free is that your private sample complexity varies asymptotically in the same way as your non-private sample complexity. And even if you don't reach that threshold, so if your epsilon is less than this thing, you still get a second term, but your second term is described as lower order, so its dependence on P and Q is lower than the first term. Okay, so it would be great if that held in general, but unfortunately that nice characterization doesn't even hold when we go up to size 3 universes. So here I have my P and my Q, and my P is just uniform in my second 2 coordinates, and my Q takes a little bit of the mass from here and moves it onto my first element. So this nice formula we had before can now be written like this. But the actual sample complexity is given by the minimum of these 2 terms. So this first term comes basically from waiting until you see an element from A, or you can tell that you saw an element for A. And the second term comes from telling between these 2 distributions restricted to B and C. And this one can be arbitrarily larger than this one. And the easiest way to see that is imagine setting epsilon to square root alpha. Then these 2 terms both scale like 1 over alpha squared, and there's no term that scales like 1 over alpha squared in this one. So we get a very different asymptotic behavior for the private test. Okay, so now we've kind of ruled out a simple characterization. Let's move on to stating the main theorem. So this is going to take a little bit. So let's start first with what our test statistic is. So remember before our test statistic we called the log likelihood ratio. And it was basically the same as this, but we didn't have these square brackets. But what I'm going to do now is for each data point, I'm going to clamp the log likelihood ratio between epsilon and this number negative epsilon prime. I'm going to talk about what epsilon prime is in a second. But basically, if it's too big, if this point was too disclosive that you were in P, you're just going to kind of scale its influence back down. And similarly, if it was too disclosive that you were in Q, you're going to scale it back up. Okay, so what is epsilon prime? So I have P and Q here. Nicely, my universe is nicely rescaled, so I have a nice picture here. And the first thing I'm going to do is this blue dotted line is the minimum of P and e to the epsilon Q. And the red dotted line is the same thing with P and Q swapped. And the important thing about these dotted lines is that their ratio never exceeds e to the epsilon. So it's between e to the negative epsilon and e to the epsilon. And what I'm going to do is take the bigger of these 2 areas, and I'm going to call the bigger one tau. And now what epsilon prime is because this area is smaller, I'm going to keep decreasing this exponent until I get area tau here. Okay, and I can definitely do that. And that is going to be epsilon prime. So notice that this lower blue dotted line and the red dotted line still have the property that their ratio is bounded between e to the negative epsilon and e to the epsilon. Okay, so now we have our test statistic. And we're going to have 2 tests that are both going to turn out to be optimal. So we're going to call this soft clamp log likelihood test. And it's basically the exponential mechanism where the clamp log likelihood ratio, our test statistic, is my utility function. So if this thing is bigger than 0, then this outputs P with higher probability than Q. And if this thing is less than 0, it outputs Q with probability bigger than P, which is the behavior we kind of want to emulate from the non-private test. The noisy clamp log likelihood test is an application of the Laplacian mechanism. So we just add Laplace noise to our test statistic, and then we do basically the non-private test. We're going to output 0 if it's bigger, output P if it's bigger than 0, and output Q if it's less than 0. And again, we have the behavior that if the test statistic is bigger than 0, we output P more often than we output Q, and the reverse if it's negative. Okay, so we're going to focus mainly on this test today, but actually both of these tests have optimal sample complexity.
They're about the same.
Sorry?
Aren't they like roughly the same thing?
Same test.
Yeah.
They're capturing very similar ideas, yeah.
But the probability distribution is not the same.
The probability distribution is not the same.
Identical.
They're not identical, yeah.
They're really similar.
Okay. So our main theorem is that both of these tests have optimal sample complexity among private tests. And we also have this characterization of the sample complexity. Okay, so what is this? So our denominator is epsilon tau. So remember, tau is this area here. Plus 1 minus tau times the Hellinger distance between P prime and Q prime. So what are P prime and Q prime? So P prime, we're going to take this blue dotted line, and we're going to normalize it. So its normalization constant is 1 minus tau. And that's going to be the distribution we call P prime. And the same thing for the red dotted line. We normalize it, and that becomes Q prime. Okay. So for the rest of the talk, I'm just going to assume that epsilon is equal to epsilon prime. The proof doesn't really change at all if I don't assume that. I just don't have to carry around this epsilon prime. Okay, questions?
I have a question.
Yes.
Why are we reducing epsilon to epsilon prime to make the areas equal?
Yeah, so what it's going to come down to in the proof is that I really want these areas to be equal because I want these normalization constants to be the same.
Okay.
We actually conjecture that you don't. The test is still optimal if you don't do that, if you just shoot between negative epsilon and epsilon. But we'll see multiple times in the actual analysis that we really do need that. Okay, so let's do some sanity checking to compare to some previous bounds. So we always know the private sample complexity should be bigger than the non-private sample complexity, and this is true. Also, for testing problems, we can use subsample and aggregate to say that the private sample complexity should never exceed 1 over epsilon times the non-private sample complexity, which is also true here. And we have one final bound to compare to. So this is this Ducci, Jordan, and Wainwright paper I referred to earlier. So they proved that the optimal sample complexity for locally differentially private tests is given by this formula here. And we know that because we're considering a superset of local differential privacy tests, our sample complexity should be better, which it is. So check. Okay. So we stated our main theorem now. So before we go into kind of the meat of the proof, let's talk about this fictional test that's going to give us some intuition for the proof. So what I'm going to do is write P and Q as mixtures. So remember, 1 minus tau P prime is exactly this blue dotted line. And 1 minus tau Q prime is exactly the red dotted line. And so to get from that thing to P, what I need to do is basically add in this green part here. So P double prime is going to be a distribution whose support is supported on just this part of my space. Similarly, Q prime is going to be only supported on this part of my space. They have disjoint support. So now imagine that you got your sample from either P or Q, and you were given the additional information that this group of samples came from P double prime or Q double prime, and this group of samples came from P prime or Q prime. Then this first problem of deciding whether it's P double prime or Q double prime, because they have disjoint support, non-privately, I would only need 1 point to decide between them. So privately, I need 1 over epsilon points to decide between them. And to decide between P prime and Q prime, these are actually, we'll see this a little bit later, but these are designed so that I get privacy for free, which is kind of going to be the first step of our proof. So what that means is that the sample complexity to determine between them is 1 over the Hellinger distance squared of P prime and Q prime. And so together, so remember this was our sample complexity before, and we can rewrite this as the minimum of these two terms, where this first term comes from determining between P double prime and Q double prime, and the second term from P prime and Q prime. So as soon as you solve one of these problems, you've decided between P and Q. And so this is our fictional test. So the proof is going to come in 3 parts. So the key inside is going to be this privacy for free for P prime and Q prime. The second part is our lower bound says that you really do need to be able to solve one of these tests to be able to decide between P and Q. And the upper bound, so remember this fictional test has this extra information of the labels of which part of the mixture you came from. And the upper bound is going to basically say that the noisy clamp likelihood test captures that test without the need for labels. So it's going to have the same sample complexity as this fictional test. Okay, so let's move on to looking at the non-private test. So we're going to need this notion here of an advantage of a test. So some test that takes in a database and outputs a decision P and Q. Its advantage is defined as the probability of a true positive minus the probability of false positive. So the probability that given a sample from P, it does output P, minus the probability that given a sample from Q, it accidentally outputs P. And a test that distinguishes between P and Q, or a test distinguishes between P and Q, if and only if its advantage is bigger than 2/3. So there's 2 conditions I had before, can just be replaced with this one condition, that this term is bigger than 2/3. Okay, remember this is the non-private test we had before. So we produced a test statistic, and then we made a deterministic decision based on that test statistic. And we're going to replace this with a randomized test. So our randomized test is going to do the same thing basically as our soft clamped test did before. But now instead of using the clamp log likelihood, we're using the actual log likelihood ratio. And the main theorem in this section is that the Hellinger distance of Pn and Qn is exactly the advantage of this test here. So this isn't too hard to prove. So let's take the time to go through this. So remember, given some database X, the probability of outputting P was by definition this ratio here. And the log likelihood ratio was exactly the log of Pn of X over Qn of X. So I can rewrite this in terms of these square roots here. Okay, now my advantage is this thing here, the true positive minus the false positive. And so by definition, this first term is the probability that you came from P times the probability that you output P. And this term is the probability you came from Q minus the probability you output P. And we can rearrange this to get exactly the square of the distance between the square roots of these two things. And this is exactly the Hellinger distance between Pn and Qn. So why is this important? So one, it kind of explains where the Hellinger distance comes from in this problem. But also, it says that the non-private sample complexity of this soft log likelihood test is 1 over the Hellinger distance squared of P and Q, which was our optimal sample complexity. So now we know that this randomized test actually has optimal sample complexity, even among non-private tests. If you're interested how you go from here to sample complexity, is that the Hellinger distance has this nice property that you can write the Hellinger distance of 2 products as the Hellinger distance of just P and Q. So we can see from this formula that if I set n to be some constant over the Hellinger distance squared, I can push this thing as close to 1 as I like. Okay, so now we've reached this privacy for free. So now we have a randomized test that's optimal among non-private tests. And also, if my log ratio is bounded between negative epsilon and epsilon, then this soft log likelihood ratio test is exactly the soft clamp log likelihood ratio test, which we proved was differentially private. So we have a private test that's optimal among non-private tests. So we get that our private sample complexity is asymptotically the same as our non-private sample complexity under this condition that our ratio is bounded. So now we have this bottom part of our fictional test. So P prime and Q prime, remember, were defined exactly so that their ratio was always bounded between e to the negative epsilon and e to the epsilon. So we get privacy for free for P prime and Q prime, and we've recovered this sample complexity that we claimed before. Okay, so we're going to go into our upper bound and lower bound now. Any questions before we go on? Okay, so let's move on to our upper bound. So as I said, we're going to focus on the noisy log likelihood ratio test. So now, remember our test statistic is the sum of these we clamp the log likelihood ratio for every data point. And now I can rewrite this like this. Now, of course, I don't actually have this information, so I can't decide whether data points came from P double prime or P prime. In particular, because I don't know whether they came from P or Q, and even if I did know that, I wouldn't really be able to do this. But for the purpose of the analysis, I can write this. And just to remind you, P prime is this blue distribution, and P double prime is just supported on this part. Okay, so the key to the upper bound proof is to note. So this is our test statistic given a sample from Q. So it's this clamp log likelihood ratio plus Laplacian noise. And we have the same thing over here, but for P. And so to prove that my test works, what I really need to prove is that this red distribution has most of its mass less than 0, and this blue distribution has most of its mass greater than 0. And I've drawn them as Gaussians here just for illustrative purposes. We actually don't know a lot about how they're distributed. But that's kind of the main thing we need, is that they're kind of separated. And so how I can describe this separatedness is I'm going to have the masses separated if the standard deviation of this distribution is less than the gap between the expectations, and also the standard deviation of this distribution is less than the gap between the expectations. So I can separate that out into three statements. So the first one is just coming from this term here. So the Laplacian has standard deviation. So I need my gap to be bigger than a constant to just get past the fact that I'm adding constant noise. And then I also need that both of these random variables have standard deviation less than the gap. So if I choose n large enough that all three of these things happen, then my test works, and my sample complexity is big O of that n. Okay, so let's look first at characterizing this gap. So the expectation under P of this thing is, so about tau n of my samples fall into this first sum, and they all cost me epsilon. About 1 minus tau n of my samples fall into the second part of the sum, and the expectation of this term, given you're in P prime, is the KL divergence between P prime and Q prime. And similarly, I can write a similar formulation where I have Q double prime and Q prime, and my expectation under Qn is negative epsilon tau n minus 1 minus tau n, the KL divergence in the opposite of Q prime and with respect to P prime. Okay, so taking the difference of these two things, I get 2n epsilon tau from here. And this Hellinger distance term comes from the fact that the KL divergence always dominates the KL divergence. So this thing is always bigger than the Hellinger distance squared. So I get this part. And now notice that what is inside the brackets is exactly the denominator in my sample complexity bound. Okay, so let's go on to my variance. So my variance I can't compute as nicely because these two terms are correlated. But I can say that my variance is less then the square of this random variable, the expected square of the random variable. And I can compute this thing exactly the same as I computed the expectation now. So tau n of my samples fall in the first thing, I get epsilon squared. But now instead of getting the KL divergence, I get a square on this log likelihood ratio here. But it turns out that this thing is less than the Hellinger distance of P prime and Q prime. And I'm assuming my epsilon is less than 1. The reason that's fine is because we know that for any constant epsilon, we get privacy for free. And that comes from the fact that we proved earlier that you're always less than 1 over epsilon times the non-private sample complexity. Okay, so now I've got that my variance is less than n times this thing, which again is the denominator in my sample complexity bound. And I can similarly prove the same thing for Q. So I have all of these inequalities where they're all n times the same term, and that term is the thing in my denominator. So now there's 3 conditions I needed before, that the gap was bigger than a constant, my variance is less than the gap squared, and this variance is also less than the gap squared. I can achieve all of those if I set n to be some big enough constant divided by this term here, because all of these become constants at that point. Okay, so if I have the sample complexity, these distributions are further enough apart that I can separate between them and my test works. Okay, so that is our upper bound. How much? Yeah.
So what is exactly the role of tau here? Do you choose it or set it to be something? Or
So I...
always valid for any tau?
No, so it was a function of P and Q. So I probably have it here. So what I did was I computed these dotted lines, which were the minimum of e to the epsilon and e to the epsilon times 1 distribution, the other one. And tau was the bigger of these 2 areas.
Right, but like is there a sort of a connection between this and the TV distance or something?
So it's smaller than total variation distance. And it can be much smaller or it can be the same. It just depends on P and Q. Okay, so the next thing we're going to do is talk about our lower bound. So what we're going to do for our lower bounds, remember intuitively for the fictional test, what we said was once you distinguish between P prime and Q prime and P double prime and Q double prime, you would distinguish between P and Q. So what we're going to do is formalize this argument that you really do have to be able to distinguish between either P prime and Q prime or P double prime and Q double prime. So remember, P and Q can be written as these mixtures of 2 distributions. And what I'm going to do is insert this distribution R that agrees with P on the second part of the mixture and agrees with Q on the first part of the mixture. And my first claim is going to be that if you want to distinguish between P and Q, you really do need to be able to distinguish between P and R or R and Q. The second part of my claim is that if you want to be able to distinguish between P and R, you need 1 over tau times the number of samples needed to distinguish between P double prime and Q double prime. And similarly for R and Q with P prime and Q prime. Okay, so let's prove the first part. So suppose I have a test that distinguishes between P and Q. So by definition, that means that its advantage must be bigger than 2/3. Which means in particular that the advantage of this test with respect to P and R, or the advantage of the test with respect to R and Q, has to be bigger than 1/3. Sorry. So let's suppose this first thing holds, that the advantage between P and R is bigger than 1/3. Then we need 2/3 here. But actually all that matters is that it's a constant. I can amplify any constant here to get up to 2/3. And the way to see that is imagine that I'm flipping 2 coins. So every time I put in a size n database here, I get a flip of one of these 2 coins. I have to distinguish between the 2 coins. Because their probabilities are a constant distance apart, it only takes a constant number of coin flips to determine which coin I have, which tells me whether I have P and R. So I just need to increase my sample complexity by a constant factor to get back up to my 2/3, which says this test works. So we have that the sample complexity for P and Q is the minimum of these two sample complexities. Okay, so the second part of the lower bound was we had to say what it was to distinguish between P and R. So remember, P and R are these two mixtures, and they agree on the second coordinate, or the second mixture part, and they disagree on the first mixture part. And suppose I have a test that distinguishes between P and R with n samples. Now I'm going to hand wave in this part of the proof a little bit, because to make this more formal, I have to use a bit more machinery than I want to set up. But just bear with me through the hand waving, and if you're really interested, the details are all in the paper. So imagine that I have tau n samples from either P double prime or Q double prime. What I'm going to do is add to that 1 minus tau n samples from P prime. And this is the hand waving part, that this is not exactly a sample from P, but it looks a lot like a sample from P or Q. But it looks a lot like a sample from one of them. So just imagine that it really is a sample from either P or Q. And what I'm going to do is put it into my test. And if my test comes out with P, then that says the original distribution must have been P double prime. And if it comes out with R, my original distribution must have been Q double prime. So this modified test distinguishes between P double prime and Q double prime with tau n samples. So what this says is that tau n must be bigger than my private sample complexity between P double prime and Q double prime. And this sample complexity is 1 over epsilon, because remember P double prime and Q double prime have disjoint support. So non-privately, 1 sample would do. So privately, we need 1 over epsilon samples. And we can make the same argument for distinguishing between R and Q. That you need 1 over 1 minus tau, the private sample complexity for P prime and Q prime, which we've already said is the Hellinger distance between P prime and Q prime. So putting all this together, we get that our sample complexity is lower bounded by the minimum of these two terms, which is exactly the sample complexity we were claiming. So to make this bound rigorous, we use something called coupling. We construct a coupling and use a style of analysis that was introduced in this paper by Acharya, Sun, and Zhang. And you can read about that or talk to me about it later. Okay, so in conclusion, what have we done? So remember, we first started with this non-private solution. That started with a test statistic, a deterministic test. It had exactly optimal sample complexity, and its sample complexity was nicely characterized. So the first thing we did was replace this deterministic test with a randomized test. And we said this randomized test has optimal sample complexity. We don't have the exactly anymore. We have asymptotically optimal sample complexity. Okay, and the main contribution of this work is this side of the table. So we modified our test statistic. So we said that what you should do is for each data point, you should limit how much it can tell you about whether you're in P or Q by clamping between negative epsilon and epsilon. And then we said your test, so we had 2 possible tests here. But we said each of these tests had optimal sample complexity. And then we characterized that sample complexity. So this, we gave this kind of closed form characterization. And we do a little more in the paper. So in the paper, we apply this hypothesis testing result to obtain optimal accuracy algorithms for the private change point detection problem. Okay, thank you.
You have 5 more minutes.
Oh, yes, I know, but I'm done.
Okay, any questions for Audra? Sorry.
I have a big question. If you go back to the previous slide, how does one come up with a picture like this?
Yeah, so the main insight, or the first insight, was this characterization of the non-private setting. So that this randomized test still has optimal sample complexity, and writing that sample complexity in terms of the Hellinger distance was kind of the first step, which said that if you did this clamping, then for this part of the distribution, you would get a private test that had optimal sample complexity, and you didn't have to pay for that sample complexity.
It's just that this would work, basically. Like the optimal test would be private.
Yes, that if you had this property, that the optimal test would be, the optimal non-private test would also be private.
I see.
I guess in some sense we started with the intuition, even initially, that some test like this should be optimal just because, like, how many other things could possibly...
I guess, yeah, you're choosing between two things. Okay, yeah, I don't know. Okay, I see.
It's a very natural test, right?
Sure.
Like to just take the non-private test, limit the influence of any one point size.
I'm not. Okay, so here's sort of my intuition about it, and I'm wondering if that is optimal or one with like epsilon delta can decide. You're basically truncating the distribution. You're considering this p prime and q prime, and you're telling each point, no, you cannot have more influence than epsilon. You're like log likelihood. And you prove that this is optimal for epsilon. I'm guessing, does this intuition sort of also translates to epsilon delta? Or can you do, like...
Yeah, so you can't do better. So this is one of the earlier slides that said that for testing problems, the sample complexity for pure differential privacy is the same as for approximate differential privacy.
Oh, it's the same. Okay.
And for any notions in between, so lots of kind of stability notions. So you really can't hope to do better if you weaken your notion of privacy or stability.
Thomas?
So usually for our hypothesis testing, we have this like power and significance parameter, which you sort of just set to like 1/3. Can you say something about the dependence on those? Is that like a black box thing you get out of it, or how does that?
Yeah, so we only consider constants. So I don't think we've really studied what can happen if you have those things to be varying. So if you want it arbitrarily close to 1, if you want that to be a parameter that you care about the asymptotics of, then we do get like log of 1 over that thing. But it's not clear that is the optimal thing to get. And then it actually comes up in the change point detection problem where that really is a parameter that you care about. So if that parameter is constant, then we get optimal things. If it's not constant, then it's not clear that what we do is optimal.
Right.
So it's more like a question about the operational meaning of tau. Do you study like is it the divergence, is it the distance, like what is the property of this tau? Is there sort of a more formal characterization, operational characterization for tau?
Right, so it has a name. It's called the hockey stick divergence.
Oh, okay.
It does not appear to be very common, but it is, and someone should correct me if it's wrong, but if you're considering P and Q just like the privacy parameters of outputting like P or Q, then it is the biggest or the smallest delta that makes that operation differentially private, which is maybe one way of thinking about it. But yeah, it may be a divergence. We're not sure. It is something we're sort of interested in because it kind of comes up.
Yeah, it's the smallest thing you can cut off the two distributions so that the remaining parts will have bounded likelihood ratios.
Satisfy pure differential. Exactly. Like it's like the minimum thing you plan, but to satisfy the e to the epsilon.
Did you use this in one of the papers? I think Marco has used this.
Yes. I think that's how we learn the name of it.
Kunal has a question.
So this truncation is also intuitively something like what you would want to do if you just wanted a robust version of a statistical test. If people in robust statistics look at similar questions.
Roberto?
Yeah, theoretically you can put you can put a bound on a robust test statistic, and this is more or less what you do, except that we never. So that epsilon would be a tuning parameter. But at least in privacy, it makes sense. In the robustness, it depends on the scale of that log likelihood. So in this case, you don't really care about that. The epsilon is naturally defined in this case, but it is linked. It exists also in robust, yes.
Great. And there is something to kind of say there. So it's not clear that epsilon. So epsilon does clamping to epsilon and negative epsilon and epsilon creates a optimal test, but it's possible you could get better constants by clamping to something else. In particular, we need this epsilon prime, and we conjecture that you can get rid of that epsilon prime, which is the one kind of efficiency caveat. And we've done some tests for whether you can make that, whether changing that parameter makes gets better constants.
Which is that open question. Any other questions? So actually, I have one question. So you started with a very simple example and practical example that we see even in news every day. People talk about, how likely, or what is the percentage of those who will be voting for Democrats, right? So based on your results, if I'm a survey statistician, I'm designing my survey, and what does this tell you about how big of a sample do I need to collect in order to answer the question you posed at the beginning?
Yeah,
maybe you want to bring up your picture, if that's easier. So practical implication.
Yes, thank you for that. So the results we have are asymptotic.
Yeah.
So if you really care about constants, which you do practically, you would really want to explore what that. I suspect the optimal test would be a clamping, but it's not clear that it would be epsilon or epsilon prime. And our sample complexity, again, is asymptotic. So if you were talking about finite samples, then it's unclear that this really tells you what you should do.
But asymptotics kick in at some point, even when we talk about small samples that people collect to do this. But I don't want to put you on the spot, but this is actually maybe a good segue to remind everyone that we have a panel set up for tomorrow afternoon. And one of the questions for the panelists does have to do with how we report the statistical results, especially with the constraints due to privacy. So something like this would be a good, perhaps, example, or something like this would be good for everyone to think about. More generally, the main questions for the panel is, first, what do we mean by the science of data analysis? And the second question has to do with how do the theoretical results, both statistical theoretical results and theoretical results from computer science literature, translate into applied methodological settings, especially when you have privacy constraints. So how do we go from these type of results basically to the question that I just asked her, and how do we communicate this with researchers, and how do we make this practical, right? And then we have some very specific questions. I think what we'll do maybe tonight, we'll email this couple of questions to everyone. In case you want to contribute in any way, you're welcome to send some questions ahead of time. But for now, we'd like to thank Audra once again.